When chemistry was an infant science, there was no system for naming compounds. Names such as sugar of lead, blue vitriol, quicklime, Epsom salts, milk of magnesium, gypsum, and laughing gas were coined by early chemists. Such names are called common names. As chemistry grew, it became clear that using common names for compounds would lead to unacceptable chaos. Nearly 5 million chemical compounds are currently known. Memorizing common names for the compounds would be an impossible task. The solution, of course, is to adopt a system for naming compounds in which the name tells something about the composition of the compound. After learning the system, a chemist, given a formula, should be able to name the compound, or, given a name, should be able to construct the compound's formula. In this section, we will specify the most important rules for naming compounds other than organic compounds. We will begin with the system of naming inorganic binary compounds, compounds composed of two elements, which we classify into various types for easier recognition. We will consider both ionic and covalent compounds. Binary ionic compounds contain a positive ion, cation, always written first in the formula, and a negative ion, anion. In naming these compounds, the following rules apply. 1. The cation is always named first and the anion second. Second, monatomic, meaning one atom, cation takes its name from the name of the element. For example, Na is called sodium and the name of compounds containing this ion. And third, a monatomic anion is named by taking the root of the element's name and adding "ide" to the end. Thus, the Cl negative ion is called chloride. These common monatomic cations and anions and their names are given in Table 2.3. The rules for naming binary ionic compounds are illustrated by the following examples. So far as we have started with the chemical formulas of a compound and decided on its systematic name, the reverse process is also important. For example, given the name calcium chloride, we can write the formula as CaCl2, because we know that calcium forms only Ca2 plus ions, and that since chloride is Cl negative, two of these anions will be required to give a neutral compound. In the binary ionic compounds considered earlier, the metal present forms a single type of cation, that is, sodium forms Na+, calcium forms only Ca2+, and so on. However, as well we will see in more detail later in the text, there are many metals that form more than one type of positive ion, and thus form more than one type of ionic compound with a given anion. For example, the compound FeCl2 contains Fe2+, and the compound FeCl3 contains Fe3+ ions. And in a case such as this, the charge on the metal ion must be specified. The systematic names for these two iron compounds are iron 2 chloride and iron 3 chloride, respectively, where the Roman numeral indicates the charge of the cation. Another system for naming these ionic compounds, as seen in the older literature, was used for metals that form only two ions. The ions of the higher charge has a name ending in "ik", and the one with the lower charge has a name ending in "aus". In this system, for example, Fe3+ is called the ferric ion, and Fe2+ is called the ferrous ion. The name for FeCl3 and FeCl2 are then ferric chloride and ferrous chloride, respectively. In this text, we will use the system that employs Roman numerals. Table 2.4 lists the systematic names for many common type 2 cations. All of these compounds include a metal that can form more than one type of cation. Thus, we must first determine the charge on each cation. This can be done by recognizing that a compound must be electrically neutral, that is, the positive and negative charges must exactly balance. Note that the use of a Roman numeral in a systematic name is required only in cases where more than one ionic compound forms, given a pair of electrons. This case most commonly occurs for compounds containing transition metals, which often form more than one cation. Elements that form only one cation do not need to be identified by a Roman numeral. Common metals that do not require Roman numerals are the group 1a elements, which form only 1+ ions, the group 2a elements, which serve special mention at this point, In virtually all its compounds, silver is found as the Ag plus ion. Therefore, although silver is a transition metal, it can potentially form ions other than Ag plus, silver compounds are usually named without a Roman numeral. Thus, AgCl is typically called silver chloride rather than silver 1 chloride, although the latter name is technically correct. Also, Roman numeral is not used for zinc compounds since zinc forms only the Ca2 plus ion. As shown in example 2.5, when a metal ion is present that forms more than one type of cation, the charge on the metal ion must be determined by balancing the positive and negative charges of the compound. To do this, you must be able to recognize the common cations and anions and know their charges. The procedure for naming binary ionic compounds is summarized in figure 2.2. The common type 1 and type 2 ions are summarized in figure 2.21. Also shown in the figure 2.21 are the common monatomic ions. We have not yet considered ionic compounds that contain polyatomic ions. For example, the common ammonium nitrate, NH4NO3, contains the polyatomic ions NH4 plus and NO3 minus. Polyatomic ions are assigned special names that must be memorized to name the compounds containing them. The most important polyatomic ions and their names are listed in Table 2.5. Note in Table 2.5 that several series of anions contain an atom of a given element and different numbers of oxygen atoms. These anions are called oxyanions. When there are two members in such a series, the name of the one with the larger number ends in ate, for example, sulfite and sulfate. When more than two oxyanions make up a series, hypo and per are used as prefixes in the name of the members of the series with the fewest and most oxygen atoms, respectively. The best example involves oxyanions containing chloride, as shown in figure 2.5. Binary covalent compounds are formed between two nonmetals. Although these compounds do not contain ions, they are named very similarly to binary ionic compounds. Notice from the preceding example that to avoid awkward pronunciations, we often drop the final O or A of the prefix when the element begins with a vowel. For example, N2O4 is called dinitrogen tetroxide, not dinitrogen tetraoxide. And CO is called carbon monoxide, not carbon monoxide. Some compounds are also referred to by their common names. Three examples are water, ammonia, and hydrogen peroxide. The systematic name for H2O, NH3, and H2O2 are never used. The rules for naming binary compounds are summarized in figure 2.22. Prefixes to indicate the number of atoms are used only in type 3 binary compounds, those containing two nonmetals. An overall strategy for naming compounds is given in figure 2.23. When dissolved in water, certain molecules produce a solution containing free He ions. These substances, acids, must be discussed in detail in chapters 4, 14, and 15. Here we will simply present the rules for naming acids. An acid is a molecule in which one or more H plus ions are attached to an anion. The rules for naming acids depend on whether the anion contains oxygen. The name of the anion ends in "ide." The acid is named with the prefix hydro and the suffix "ix." For example, when gaseous HCl is dissolved in water, it forms hydrochloric acid. Similarly, HCN and H2S dissolved in water are called hydrocyanic and hydrosulfuric acids, respectively. When the anion containing oxygen, the acidic name is formed from the root name of the anion with a suffix of "ic" or "us", depending on the name of the anion. If the anion name ends in "ate", the suffix "ic" is added to the root name. For example, H2SO4 contains the sulfate name SO42 negative and is called sulfuric acid. H3PO4 contains the phosphate anion PO43 negative and is called phosphoric acid. NH2H3O2 contains the acid ion C2H3O2 negative and is called acetic acid. If the anion has an "ite" ending, the "ite" is replaced by "us". For example, H2